Hello, this is Math 2520 and this video is over section 8.3. And in this section we will be looking at doing integrals that involves trig functions, more than just the basic trig functions. So for instance, if we want to evaluate tangent squared and integrate that, we'll have to learn new methods to do this. Often when we have integrals that have higher powers of trig functions, we need to use some trig identities to solve them. So some of these you should remember from pre-calc. Basic ones: sine squared, cosine squared equals 1 when added. 1 plus tangent squared equals secant squared. 1 plus cotangent squared equals cosecant squared. Then there's the power reduced formulas, there's double angle formulas, and then the summation and difference formulas for sine and cosine. Now, one thing to notice in a lot of these is when you see sine and cosine, they're usually together. When you see tangent and secant, they're usually together. And when you see cotangent and cosecant, they're usually together, based on how these identities relate to each other. And so when we are looking at these strategies, we're going to look at them kind of in pairs. Powers of sine and powers of cosine together, powers of tangent and secant, and powers of cosecant and cotangent. I will say that there's kind of a method to doing this, and it does kind of stay consistent, but each one has little nuances that you have to kind of get your head around. And that's going to be what's probably the most confusing part of it. So let's start with evaluating a integral that has sine to some power and cosine to some other power. We're going to look at 3 different cases. If the power of cosine is odd, then we have to save one of the cosine factors and then use a substitution of w equaling sine x. Okay, and so the reason we have to do this is when we differentiate w, we get dw equals cosine x, and we're going to be able to make a substitution. We'll also have to use cosine squared x equaling 1 minus sine squared x. Alright. If the power of sine is odd, then we save one sine factor and use sine squared x equaling 1 minus cosine squared x. And then substitute in w equals cosine, so that way dw equals a negative sine x dx. And in the last case, if both powers of sine are even, then we have to use our power reduction formula, sine squared x equals 1/2 1 minus cosine of 2x, or cosine squared x equals 1/2 1 plus cosine of 2x. Okay, notice, except for case 3, we are preparing our integrand for substitution. Alright, so let's do a couple of examples. Cosine cubed and sine to the negative 2 power. And we want to evaluate this. Since cosine is odd, we are going to save one cosine factor and use cosine squared equals 1 minus sine squared. So we're going to rewrite this. Cosine x, cosine squared x, and then sine to negative 2x dx. Okay, and then for this cosine squared, that's going to become 1 minus sine squared x. Okay, so we'll have the integral of cosine x times 1 minus sine squared x sine to the negative 2x dx. Now we plug in where we will have our w. So we're going to let w equal sine x, dw equal cosine of x dx. So this is going to be our dw, and then w equals sine x, so we'll have this be w squared and this be w to the negative 2. So this is going to become 1 minus w squared w to the negative 2 dw. Now we can distribute. So w negative 2 minus w squared times w negative 2 dw, which will be w to the negative 2 minus 1 dw. Okay. Now we have it something where we can integrate. So when we integrate w to negative 2, that power goes up to negative 1. We divide by negative 1. So our w to negative 1 over negative 1 minus w plus c. Can't forget our constant. And so now we can rewrite this negative 1 over w minus w plus c. And then if we insert sine back into this, negative 1 over sine x minus sine x plus c. And then finally 1 over sine x, this is cosecant. So we can say negative cosecant x minus sine x plus c. Okay, take some algebra to work your way through, but it is doable. If there isn't a sine function, that's the same thing as sine being even. So in this next case, we will have cosine to the 4th. So cosine's not odd, so we can't use the method we just used. And both cosine and sine can be considered even. So what we have to do is we have to do case 3. So what I'm going to do is adjust this so it's cosine squared x squared dx. And then remember, we're going to have to use this formula. So we would have cosine squared being 1/2 1 plus cosine of 2x. So this becomes, I remember what I said, 1/2 times 1 minus cosine of 2x. That whole thing squared dx. Okay. And so let's do some simplifying with this. 1/2 squared is going to be 1/4. I can actually bring that out. And then we have 1 minus cosine of 2x being squared. So I will write this out this way so I can FOIL it. And yeah, no parentheses there. And then dx. So now we'll FOIL. So 1 times 1 is 1. Then there's negative cosine 2x, and negative cosine 2x is negative 2 cosine 2x. And then positive cosine squared 2x. dx. Now, what we notice here is we have another cosine squared. So we have to use that same substitution again. So this is going to be 1/4 integral of 1 minus 2 cosine of 2x plus, and that is 1/2 1 minus cosine of 4x, since you have to double the x when we do this, squared. Oh, sorry, not squared. I'm like thinking that's going to make this really hard. So the dx. I was thinking squared because I had up top here, I had it squared. So now everything's a basic cosine. So now this is actually, we're almost there at the end of the problem. 1 minus 2 cosine of 2x, distribute the 1/2. We'll have 1/2 minus 1/2 cosine of 4x dx. And so we can integrate each of these. When we do, the first one will be x, and then 2 cosine of 2x. When we integrate that, we'll get sine. So we'll have 2 sine of 2x, and then just gotta make sure this works out, because when we take the derivative of sine of 2x, we'll get cosine of 2x, but also multiply by 2. And we don't want that, so we have to divide this by 2, which actually will cancel these out. So sine of 2x, when you do the derivative, you get 2 cosine of 2x. And then we'll have 1/2 x. And then this also will be a sine of 4x. When we take the derivative, we have a 4 come out. So we actually have to divide by 4 as well. So we'll have it as an 8 on the bottom. All right, we're almost done with this whole thing. I'm going to distribute the 1/4 as well. And we can put some things together. Certain things can't go together. Like the sine of 2x and sine of 4x. Those have to be separate terms. The main term I'm going to look at, I'm going to do this off to the side. 1/4 x and plus 1/8 x. That we have to adjust. And so that's going to be 2/8 x plus 1/8 x, which is going to be 3/8 x. So the first term is going to be 3/8 x. Then minus sine of 2x. And then minus sine of 4x over 8. I'll make sure. You know what? I do have a sign error, I noticed. Let me just adjust that. It didn't affect too much. Those should all be pluses. That stays plus. Just with these. I had switched the sign when I did it. Instead of having that be positive here, I had that be negative. Luckily, it didn't cause much of a problem. All right, so now we'll do, that's the final answer. Now do sine to the fifth. And so what we're going to do is break this up into sine x sine to the fourth x dx. And sine to the fourth, we'll break that into sine squared x squared dx. And sine to the fourth is the same thing as sine squared times sine squared. And then sine squared x, we'll let that be 1 minus cosine squared x being squared dx. Now we let w equal cosine x and dw equal negative sine x dx. And so we can make this into the integral with w's. So anywhere we have a cosine is a w. The sine x and dx is going to be this. So this is going to actually equal negative dw. So we'll put a negative on the outside. And 1 minus w squared dw. Okay, so we can FOIL this out. We get 1 minus 2w squared plus w to the fourth dw. Then we can integrate this. So the negative on the outside for right now, w minus 2w cubed over, oh wait, what? Yeah, 2 cubed over 3 plus w to the fifth over 5 plus c. And then last step I'll do in 2, I'll distribute the negative sign, and then I'm replacing the w's with cosine. So negative cosine x, positive 2 cosine cubed x over 3, negative cosine to the fifth over 5. Taking a long time to save. There we go. Negative cosine to the fifth x over 5, and then plus c. You don't have to distribute the negative sign to the plus c, because that's not something you have to do. I mean, we could distribute that negative sign before we even put the plus c, so it's always just going to be plus c. Right. So those were powers of cosine, powers of tangent. They were when sine is odd or cosine's odd, and then when cosine or tangent's even. And as you saw, is if they have any sine when they're even in the third problem, we had a sine even, but then we also had a sine odd. It didn't cause a problem. So those were the 3 cases we had to look at. The next one's going to be tangent to some power and secant to some power. And it's going to be very similar. We're just using stuff with tangent and secant instead of cosine and sine. So first we look at if the power of tangent is odd and you have at least one secant. Then we save one secant x tangent x factor and use tangent squared x equaling secant squared x minus 1. There is one thing that's separate with this. We will need a secant involved with this, so you can't just have tangent to a higher power in this particular case. And so with this, the rest of the terms will only be in terms of secant, except for the one that we save with the tangent, and then we can substitute in w for secant x, and dw then equals secant x tangent x. That's why we need to save one of them. And that's case 1. In case 2, if the power of secant is even, then we save a secant squared factor and use secant squared x equaling tangent x plus 1. And then we'll do it in such a way where the rest of the integral is only in terms of tangent, except for that secant squared factor. And then we use w equals tangent, where dw equal your secant squared x, which is why we gotta save it. And if case 1 and case 2 don't apply, you need to be creative. Something like tangent squared x would be one that it wouldn't apply. We may have to use substitution. We just don't have cases for those. So we want to evaluate tangent cubed secant x. And this one has tangent being an odd power, so we have to save a tangent secant. So our tangent squared x, tangent x secant x dx. And so our tangent squared x, we use our, I'm going to keep this up here actually, our tangent squared x equaling secant squared x minus 1. So we'll have secant squared x minus 1 tangent x secant x dx. And then we're having w equaling secant x. So dw equals secant x tangent x dx. So that's this part. That's your dw. And then this would be w squared minus 1. I'm going to actually bring that closer together here. Right. And so now we can take integral w cubed over 3 minus w plus c. I don't need the integral sign anymore. Right. And then we let w equals secant cubed, or w equals secant, so this will be secant cubed over 3 minus secant x plus c. And that's your final answer. Okay, so if we want to integrate secant x, we would have to look at this being case 2, right? Well, I'm sorry, that's even. Oh, I know what. Okay, yeah. So this is not one of the cases right now. This is where we have to be a little bit creative. So what we were going to do with this one is actually multiply it by secant x plus tangent x over secant x plus tangent x dx. This is where the creative part comes into play. It almost seems like, why would we do that? Well, we're trying to get something where we can use that rule, and this will turn out to be the best way of doing it. So when we distribute the secant x, we get secant squared x plus secant x tangent x all over secant x plus tangent x dx. And then here we'll do a u substitution. U equaling secant x plus tangent x. So du equals secant x tangent x plus secant x squared dx. That means the top is your actually what you have for du. The bottom is what you have for u. And we can integrate that and we get natural log of u plus c. And so we'll end up with the natural log of secant x plus tangent x plus c. This actually is going to come in handy because we're going to be integrating secant x a few different times throughout the semester. So if we want to evaluate tangent cubed secant squared x, what we will have to do is, for this one, let's see, tangent is odd and you have at least one secant x. So we will save a secant tangent. So let's set that aside. So we'll have integral of tangent squared and actually, hold on, let me see something important. Trying to think of the best way of doing this because secant is even also. So I think the best way with this, actually, not going to be that way. That's going to get really complicated. I think the best way is this, let w equal your tangent x, and then dw equal your secant squared x dx. And so we end up with w cubed dw, which is much easier to integrate. W fourth over 4, which is going to become tangent x to the fourth over 4 plus c. If we tried it the other way, see how bad this gets if it gets bad. Tangent. I think what we will want to do is have this be tangent x and then keep two factors of tangent x secant x. So we can write this as tangent x secant x squared dx. And then we're letting w equals secant x, but we don't have a secant x left over. Yeah, you have to save one. So I don't think that will work out. Yeah, it's not working out with that way. So this way is the best for this example. All right, I don't want to spend too much time spending wheels on that. Let's do tangent squared x secant to the fourth. Oh, you know what? That's what. Okay, I know we can do it the other way. That's something I was forgetting. Let me rewrite this one. Now I'm invested in it. So if we break this into tangent squared x and secant x, and then tangent x secant x dx. The tangent squared x we would have to break into, and that's what I was kind of forgetting to do. The tangent squared x equaling secant squared x minus 1. So this is secant squared x minus 1. And then times secant x times secant x tangent x dx. And so we let w equal secant x, so we'll have w squared minus 1 times w times dw. Okay, so with that, w equals secant x, dw equals secant x tangent x dx. So that's that part. And now this is something we can solve. So we'll distribute w cubed over minus w dw. And then, oh, wait. Yeah, that makes sense. Okay, so take the derivative, you have w to the fourth over 4, w squared over 2. And we can have then switching it back to secant to the fourth x over 4 minus secant to the fourth, but squared x over 2 plus c. They're a little bit different. They're different for sure, but we would have to show that those two eventually end up being the same to show that these are equal. But just kind of know that secant and tangent are related enough that chances are we can prove that these are equal. But each one will take you in a little bit different direction. All right, so the last one with this, tangent squared x secant to the fourth x. Here we are going to break secant. Let me think the best way to do this. Break secant x up. We're doing that first. So tangent squared x, secant squared x, and then secant squared x dx. And then we'll make one of the secant squared x. We'll make tangent squared x plus 1. And then we'll let w equal tangent x, dw equal secant squared x dx. So this is our dw. And then we'll have tangent x, so we'll just put in w for that. So w squared w squared plus 1 dw. Then some simplifying. And then we'll take the integral. So we'll do w to the 5th over 5 plus w cubed over 3 plus c. This is going to give us tangent to the 5th x over 5 plus tangent cubed x over 3 plus c. Alright. I'm going to make this video into 2 parts. There's a lot to it. We still have to cover cotangent and cosecant. And there's some additional problems we can look at. So I'll do that in a separate video. So that way this is kind of broken up into 2 parts. Alright, I'll see you in the next video. Bye.